and thank you so much for coming and spending part of your Saturday with us. I hope you'll have a lot of fun. And so, as Joanna said, I am a scientist from France, and the Lawrence Livermore Lab is famous even all the way to France. So I joined the lab 10 years ago, and as a kid, I wanted to be either an astronaut or an orthopedic surgeon. So today I'm neither of that. Because someday, during my studies, I discovered the wonderful world of using lasers and plasmas to do research. And so I decided to go into that path, which took me to the lab today. So today we'll talk about lasers and plasmas, and I even have a little surprise for you during the talk. You guys will help me to make a laser. And then the movie that we'll see after that, Real Genius, is about a student at a university working with big lasers, just like what we do at the lab, which is why I chose that movie that I enjoyed a lot as a kid. So the movie came out when I was a kid, and I wanted you to share that fun movie today. So, in order for us to understand what is a laser plasma accelerator, well, let's try to look at particle accelerators, what they do and what they are. So what are particle accelerators? So particle accelerators are big machines. They're very big. I have one of them in the back on the left-hand side of the slide. It's called the Large Hadron Collider, or LHC. It sits at CERN in Switzerland, near Geneva, and it is used to accelerate particles in order to make new discoveries. And you can see on that picture that that accelerator is so big that it's about the size of an airport runway. It's about 27 kilometers in circumference. And I like to compare that to the size of a big city. So that particular accelerator is the size of a big city like Paris in France. So the particle accelerator are very important for a lot of things. There are about 30,000 of them today in the world for various activities. And these particle accelerators are used, for example, for fundamental discoveries. They can help discover new particles and to confirm physics theories. They can be used for medical applications. They can be used for curing cancer, for diagnosing diseases. They can be used for industry. They can help people in industry manufacture the chips that are in your telephones. And some of them also can be used for national security applications. They can be used to produce radiation to help diagnose threats from entering into the countries at airports or ports. And so particle accelerators, like their names say, are made of particles. So where do we get those particles? Well, particles come from what we call the elements. So elements are things that surround us. Let's take a few examples. For example, you have the water that you drink. It's made of the elements hydrogen and oxygen. The air that you breathe is made for the most part of the element oxygen and nitrogen. Diamond, which is very common also, is made of the element carbon. And finally, some of the pipes that you have around your houses are made of the element copper. So if we're to take a look closer at some of these elements, we would see something like this. The elements contain what we call atoms. Atoms is the smallest form of matter that retains the property of a given element. And to give you an idea of how small an atom is, 1 carat diamond, which is about the size of my engagement ring, contains about 10 to the 22 atoms of carbon. So it's 1 with 22 zeros behind it. So that's a lot of atoms. So atoms are tiny, tiny, tiny. And if you're taking a closer look at what an atom looks like, it's made of 2 main parts. The first one is called the nucleus, which is in the middle, and the nucleus is made of 2 types of particles. It's made of protons, which have a positive charge, and it's made of neutrons, which have no charge. And around that nucleus, you have other particles orbiting. These particles are called electrons. And in an atom, there are the same number of electrons as the number of protons, so that overall, an atom has no charge. And also, the number of protons and electrons that you have in an atom will tell you what you have as an element. For example, the element helium, which is the gas that you put in balloons, has 2 electrons and 2 protons. So now that we have our particles, we know where they come from, let's take a look at how a real particle accelerator works. And so for that, I'm going to take you very close to here in the south of the San Francisco Bay Area, where we have a big particle accelerator at the SLAC National Accelerator Laboratory. That particle accelerator, it's so big that you can see it from the airplane if you land in San Francisco, and it's called the LCLS, Linear Coherent Light Source. It is 3 kilometers in length. It is very big. It's linear. If we take a closer look at what's inside, here is how it works. So we have a laser, and it's shown here as little red blobs coming into the pipes, and it's shining onto a piece of copper to extract some of the particles from the copper atoms here. And then the electrons, which are the blue balls on the movie, are coming out of that piece of copper and launched into the machine. When they're launched into the machine, then they're pushed by accelerator sections, which have a very powerful electrical field. They're also bent around using powerful magnets, and so this is what you can see here. And eventually, once they have undergone a number of things, they're finally pushed by the accelerator, by the electrical field of the accelerator, to very high velocities. Particles in a particle accelerator go so fast that they reach velocity that are very close to the speed of light. That is 300 kilometers per second, so that's very fast. One of the things that scientists like to do with a particle accelerator is to make X-rays. So what are X-rays? You probably have all heard about X-rays. You've been to the doctor or to the dentist to have a picture of your teeth or your body taken using X-rays. So let's take a look at what X-rays are. So X-rays, it's just like the light that you see here. It's like the light from these projectors. It's like the light from the sun, except that you cannot see X-rays. So scientists have a very particular way to describe light, or we call that, more generally speaking, radiation. The way we describe radiation is by picturing it as a wave that carries energy. And the distance between 2 crests of that wave carrying energy is called the wavelength. And the wavelength will determine which type of radiation we're dealing with. If the wavelength is about the size of a big building like the State Theater here, we're saying that we have radio wave. This is the same type of radiation that you have to listen to the radio in your car. If that wavelength then is smaller, about the size of a human body, we have what we call microwaves. These are the waves that you have in microwave ovens to heat your lunch. If that wavelength gets even smaller, the size of a honeybee, we have infrared radiation. This is radiation that is emitted by our body, which is why we can look at our bodies with infrared cameras when we are in the dark. If that wavelength becomes even smaller, so that it's the size of a big bacteria, we have what we call visible light. And this is the colors of the rainbow. This is the light that you can see with your eyes. That's the only form of radiation that you can see with your eyes. Then if the wavelengths become even smaller, then we have what we call ultraviolet radiation. And if the wavelength is so small that it's about the size of an atom, then we have what we call X-rays, which is why the X-rays are so powerful. And we can even go further, even smaller wavelengths, such as we have the size of a nucleus, the middle of an atom, we have what we call gamma rays. So X-rays are a very powerful type of radiation, and it allows you to do different things than the light you can see. What can we do with X-rays? We can take pictures inside of things, because X-rays penetrate through different objects. They can penetrate through your body, so that we can take pictures of your bones, of your teeth, to diagnose if you have something broken. But X-rays are also used at airports. We can look at your luggage, and you can see that this person has a nice bottle of wine inside of a suitcase. And X-rays can be also used to look at inside of things such as this remote here, and this is what it would look like in an X-ray image. So X-rays are very, very powerful. So now, how do we make X-rays using a particle accelerator such as the one I've showed you in my previous slide? Let's take a look. For that, we have to understand that a particle, such as an electron, that is going to travel very fast and that it's changing direction, is going to emit radiation. So let's try to understand this. Let's say you're driving on a road very fast, and all of a sudden you have to make a turn. If you're coming too fast into the turn, you'll keep going straight. So the particle is the same. It's going to want to keep going straight when you want to make it turn. And so it's going to give it away in the form of radiation in the straight direction. So the particle turning is emitting radiation along the path that it wants to go to. In a particle accelerator, how do we make the particles change directions? Well, for that, we use magnets. So magnets have the property of making particles change direction. So here on this picture, if we have an electron that's traveling at a very high speed, like in the SLAC particle accelerator, and if it's coming through a series of magnets that we alternate in a certain way, so N and S means north and south on the picture, so we change their direction, so that the particle is going to go up and then down, and then up and then down, and it's going to wiggle. And when it does that, it emits X-rays. So now I'm going to try to go a little bit in more details about why a particle is emitting X-ray radiation and not visible light, right? So what I've shown you here is that a particle that is wiggling between magnets is changing direction and is emitting radiation. Why X-rays and not visible light? Well, let's try to take a look. If you see the size of a particle accelerator magnet, it's about a centimeter. It's about the size of my finger. It's about the width of my finger. But wait a minute. When I told you about wavelengths, the X-ray wavelength I mentioned is the size of an atom. So it's much smaller than this. So if we go back to our radiation spectrum that I showed earlier, we saw that we have different types of radiation characterized by a wavelength. If we take a closer look, the size of this magnet particle accelerator, it's about a centimeter. It is about the wavelength of microwaves, so it's much bigger than X-rays. It's much bigger than X-ray wavelengths. So how do we go from something that big to something that small? Make something that small with a small wavelength like X-rays? Well, in order to do that, I'm going to need some help, and I'm going to need some help from a very famous physicist. I'm going to need some help from Albert Einstein. He's going to give me a hand here to explain why we get X-rays and not visible light in a particle accelerator. So among the many clever things that Albert Einstein did during his career, he derived a theory called the special theory of relativity. The special theory of relativity has taught us three things. The first one is that nobody, even on 580, can go faster than the speed of light. So, nobody, not even electrons. So everybody is limited to the speed of light. The second thing is that somebody who will go at very close to the speed of light, let's say 99.9% the speed of light, will look like a shrunk person. So let's say today I'm around Modesto and there's a traffic officer in the street. I love biking, so sometimes I do a lot of bike riding on the weekends or at lunch, and I'm passing by that officer. So when I pass by that officer, let's say today I'm very strong and I decided to go to 99.9% the speed of light. The officer is going to see me like a shrunk cyclist. I'm going to be shrunk about 10,000 times if I go as fast as particles in a particle accelerator. The third thing that the theory of relativity from Einstein has told us is that, well, the officer is going to see me shrunk, but relativity says everything is relative. So in my case, I am going to look normal. I'm not going to think that I'm 10,000 times smaller than what I am. But I am going to see the officer shrunk because I go by very fast when I pass by him. So everything is relative. He sees me shrunk, but I see him shrunk. So how does it apply to our particle accelerators? Let's go back to it. This is our electron going to 99.99% the speed of light, entering the magnets. The magnets are a centimeter, but as we said, the theory of relativity is going to make it so that the electron is going to see shrunk magnets. So something about 10,000 times smaller. Where does that take us? It takes us from the wavelength of microwaves to the wavelength of visible light. We're not there yet, but almost. We have one more step. So the electron that is wiggling in the shrunk magnets is going to emit radiation. That radiation, when it's emitted by a particle moving very fast, it's going to have something that we call the Doppler Effect. So the Doppler Effect, you've all probably experienced this in your everyday lives. When you have an ambulance coming at you or a fire truck coming at you, it's making some noise. And when it's coming at you, it's having a higher pitch. When it's leaving you, it has a lower pitch. I can make that sound for you if you want. It says, yeah, very good, thank you. All right, so it's the same thing for radiation. The electron is emitting wave, and because the electron is traveling very fast toward me, that wave is going to look shrunk. It's going to be 10,000 times smaller. And there we have our X-rays. So this is a very powerful method to try to make X-rays with particle accelerators. And we have particle accelerators that make X-rays that we like to use as scientists. I'm going to give you two examples. The first one on the left-hand side is a synchrotron. It's a big ring that's about the size of several football stadiums. And the second one, which is the one I showed you earlier at the SLAC National Laboratory, it's called an X-ray free electron laser. These two particle accelerators uses the electrons that they produce to make X-rays, as I explained to you in the previous slides. And why are X-rays so important for us scientists? They're very important not because they can penetrate through bodies and airport luggage, but because their wavelength is so small, is the size of an atom, they can look at atoms. Our eyes cannot see atoms, but X-rays can. So here, this is an example, for example. Well, we can take water, for example. It's a molecule. It has 2 hydrogen atoms and 1 oxygen atom. And what scientists like to know is how molecules arrange themselves and form themselves. These type of thing, it happens on a very, very tiny scales. So X-rays can help you to look at that. But molecules and atoms also have the property to arrange themselves very, very rapidly. So how fast exactly? Faster than the blink of an eye, you think? Yes. It happens in what we call a few femtoseconds. So what is a femtosecond? It is a quadrillionth of a second. So it's much, much, much smaller than a second. So to explain you a little bit what a femtosecond is, if you want to compare a femtosecond to a minute, it's like you compare a minute to the age of the universe, which is 14 billion years. So femtosecond is extremely, extremely small. And for example, if you take some light and you want to send it to the moon, it will take you about 1 second to send that light from the Earth to the moon. In 1 femtosecond, it will barely have time, that same light, to cross the width of one of my hair. So that's to tell you how fast a femtosecond is. But because molecules and atoms are really fast, arranged really fast, we need X-rays to look at them, and we need these X-rays to last for only a few femtoseconds. So the big machines that I showed you, the synchrotrons and the free electron lasers, what exactly are they showing us? What X-rays are they giving us? Well, synchrotrons, they have a collection of many X-ray wavelengths at the same time, which is good, but they're also very slow. They last longer than a few femtoseconds. So they'll allow us to see atoms and molecules, but they don't allow us to see how they arrange themselves. On the other hand, the other type of X-ray machine, the free electron laser, it produces X-rays that only have one wavelength at a time, so you cannot do as many experiments as you would with a synchrotron. But on the other hand, these X-rays are very fast. They last for only a few femtoseconds, so we can look at atoms and molecules arranging themselves. Another thing also is that the synchrotrons and the free electron lasers, they're big. You cannot have them in your garage or your dining room, right? So wouldn't it be nice to have an X-ray machine that has several wavelengths, that has femtosecond X-rays to allow you to look at molecules and atoms, and that you can fit in your garage or your dining room? Yes. And this is what I'm going to show you next. How do we accelerate particles, but on a much smaller scale? We do this by using a technique that is called laser weak field acceleration. And for that, we need lasers and we need plasmas. So on the left-hand side, you have a regular particle accelerator, like the one at SLAC, in the south of the bay, and it's 3 kilometers in length. On the right-hand side, you have a laser plasma accelerator, on which I am working with one of my colleagues at the Lawrence Livermore National Lab, and it's about the size of a human person. So in order to understand why this is so important to have small accelerator, well, we'll take a look at the things that we need for that. And we need lasers and we need plasmas. And this happens on a much smaller scale because the electrical field that pushes the particles in a plasma accelerator is about 1,000 times stronger than what it would be in a regular particle accelerator. So first of all, we need lasers. What are lasers? So you've probably all heard about lasers in your daily lives as well. There's something that is used for laser eye surgery. You can correct the shape of your eyes. It's also used at the register when you want to pay for groceries. It's used to read CDs, to listen to music. And lasers, actually, it's an acronym. It stands for Light Amplification by Stimulated Emission of Radiation. So how can we explain how lasers are powerful? If you take a light bulb or a projector, and if you try to look at it in many directions, you'll see the same thing. And it also has many colors. It emits a lot of different colors. Well, now, if you could take all of this emission from the light bulb and put it into one color and one direction, we have what we call a laser. And so you're going to see in the movie that lasers can be very powerful. I will give you a little spoiler. Some scientists in the movie use that to make popcorn, so you'll have to see. But right now, I'm going to need your help to make a laser. So, I think you guys are doing a very good job listening to the talk so far, so I want all of us to give us a big round of applause. All right. So, you don't know it, but you've just made a light bulb. So now, let's try to make a laser. So you see that noise was a little bit fuzzy. We were all clapping in different times, and so we made some noise, but we can make more. So now, let's try to clap all together at the same time in the same rhythm. So you can see that we make much more noise that way. It's the same thing when comparing lasers and light bulb. When the light is all organized and what we call that coherence, then we have a laser. When the light is just all over the place, we have a light bulb. So thank you guys, you've just made lasers. And in the movie, you'll see a lot of these as well. All right, so now the second thing that we need is a plasma. To a laser plasma accelerator. So what is a plasma? If you take an atom, just like what I showed at the beginning of the presentation, we can actually separate the different particles. Let's take an example with a simple atom, helium. It's the same thing as what you have in balloons. Helium has 2 electrons and 2 protons. If you bring enough energy onto an atom, such as the light from a laser, you can separate the electrons from the nucleus. It's the same thing if you have a rubber band. If you pull on it a little bit, if you pull hard enough, you'll just break it apart. Same thing for an atom if we use laser light to break it apart. And what you're left with is a soup of electrons in yellow and proton neutrons in blue and red. And so we call that a plasma. It's a state of matter where electrons and the nucleus from the atom have been separated but are moving around each other. In a plasma, electrons are about 1,000 times heavier than the nuclei. And so because of that, when you're going to try to push through your plasma, the electrons are going to move around a lot faster than the nuclei would. So these nuclei that have been stripped from their electrons are called ions. And comparing the mass of electrons to the mass of ions is exactly like comparing a bowling ball to a ping pong ball. So if you were coming into a sea of bowling balls and ping pong balls with a blower, your bowling balls wouldn't move, but your ping pong balls would. If you're coming with a laser through a sea of electrons and ions, in our case, the electrons are going to move and the ions are going to stay where they are. They're going to be immobile. So what happens exactly now that we have our laser and our plasma if we send more laser light through that plasma of electrons and ions? So ions are not moving, and so the laser is going to make the electrons move. It's going to make the same thing as what a boat would do on a lake. So when a boat is driving on a lake, it's going to create something at the back, which is what we call a wake. It's creating a wake. Well, in a plasma, you don't have a boat, but we have a laser pulse. This is what it's shown in green. And it's going to push through the electrons of the plasma. And this is going to do this. It's pushing through the electrons of the plasma, just like a snowplow. It's going to move the electrons away. And we have what we call a laser wave field accelerator. So this is very small. This is about the size of a human hair in length. And now that we have created that wave at the back of the laser, just like a boat would create a wave in its back on a lake, if some electrons can be placed at the top of the wave that we have created with our laser, what do you think they can do? they can do something very popular in California. They will surf. So we have electrons that can surf what we call the plasma wave. Let's see how it works. So we begin here with a very, very big wave, just like a wave in the ocean, except that it's made of electrons. It's going to become so important and so high that it's just going to break, just like white water. And then some of these electrons are going to be trapped on that wave, and what they're going to do, they're going to be able to surf and be accelerated to very high velocities, just like in a regular particle accelerator. So now I'm going to show you two different examples of particle acceleration using surfing as an illustration. And just like surfing, particle acceleration, it requires very good synchronization. It means that you need to have enough momentum to catch the wave at the beginning. So we'll see here, we have a sea, we have a lot of electrons, these are surfers, and we have a wave, which is our plasma wave that is coming. So the surfers, or the electrons, that do not make any effort to paddle are not going to catch the wave, but you're going to see one of them very cleverly is catching the wave, and when he does that, he accelerates and gains energy. So that's an example of a very powerful accelerator because it has a very powerful wave and a surfer, or an electron, that is well placed in the wave. Now let's try another example of particle acceleration. So when I moved to California, I was told that surfing is the thing, so I tried. And alright, here I am sitting on the waves, but see, if I don't paddle, if I don't do anything, the wave is passing and no acceleration. So finally, if the electron decides to move a little bit around, he's trying, it's hard, and if he has enough momentum and speed, yes, he can catch the wave. But that was a small wave, so it didn't go as fast as the pro surfer on the other movie. But still. So electrons gain speed just like a surfer would gain speed on a wave in the ocean. Unfortunately, our daily jobs at the lab is not about surfing. I wish we could surf. But we do these experiments using lasers. And we have two of them here. The one on the left-hand side is called the Callisto laser. And the other one is called the Titan laser, and they're part of a nice laser facility that we have at the Lawrence Livermore lab called the Jupiter Laser Facility. And here we are with our happy team doing experiments on the lasers. All right, so we've seen how we can accelerate particles using lasers and plasmas. Now, let's see how they can make X-rays. So in order to understand how these particles in our laser plasma accelerator make X-rays, let's remember how to make X-rays with a regular particle accelerator. I told you earlier that electrons that are wiggling inside of magnets will emit X-rays. Well, we don't have magnets in our laser and plasma accelerators, but we have something else. What are the electrons going to do? Instead of having magnets to make them wiggle, they're just going to use the strength of the wave they're surfing on. They'll just do like this wakeboarder. This wakeboarder is just using the wave to accelerate, but also to wiggle. So it's just making this motion like this. So it's going to move forward, but it's also going to wiggle. The electrons do exactly the same thing. And so we can take a look at an illustration that shows you how the electron do the same thing as the wakeboarder. So this is our electron plasma wave, and this is our laser pulse. So this is the same thing as our boat, the wake at the back on which the wakeboarder was. And so the laser pulse is going to make an electron trapped into the wave, just like our wakeboarder. And that electron, just like the wakeboarder, is going to accelerate in the wave and is also going to wiggle at the same time. And so what is an electron accelerating to near the speed of light and wiggling? It's emitting X-rays. And this is what we're doing here. And this type of X-ray source, it's another X-ray source that we have created at the lab, and we call that the Betatron X-ray source. And this is a picture of what it looks like in reality. And this is a picture of how we make it in the lab So here we have a laser that we bring in with a big set of mirrors. You'll see in the movie that lasers can be directed where you want using mirrors. And we send that onto a little piece of gas cell that is filled with the helium gas that I showed earlier. And we create our laser plasma accelerator and make X-rays with it. And you can see that it fits on a table where I'm working with one of my colleagues at the lab. So now, let's take a look at our different X-ray machines that we have talked about through this talk. We talked about synchrotrons and free electron lasers, which use big particle accelerators and big magnets to produce X-rays. And I have showed you that we can use lasers and plasma to do something that is called a laser wake field accelerator. And that laser wake field accelerator emits X-rays as well, but on a much smaller scale. And earlier, I also told you that synchrotrons and free electron lasers emit X-rays that have some properties. Synchrotrons have X-rays that have several wavelengths, but they're very slow. They cannot look at water molecules arranging themselves. Free electron lasers only have one wavelength at a time, but they're very fast. They can look at molecules and atoms arranging themselves together. And our X-ray source created with the laser wake field accelerator, well, it has the best of both worlds. It has many wavelengths, and it also has fast X-rays. So it's able to look at atoms and molecules arranging themselves together. And so finally, to conclude the talk, let's try to look at some of the applications that we can make with X-rays from our laser wake field accelerator. The first one, it's X-ray radiography. So you've all been to the doctor or the dentist to have a radiography taken. So a radiography, it's a picture, but taken with X-rays. So if you have your hand and you send X-rays onto your hand, then you can see an image of the X-rays passing through your hand if you have a detector behind it. And this is what it looks like. X-rays are so powerful that they can penetrate through matter and through your body. So you would see the inside of your body, in this case your bones. With the X-rays that we produced with our laser plasma accelerators, we can look at even more details inside objects. And so here, these are two examples of research that we do. We can use the X-rays to look at very fine details in insects, such as the one I am showing on the screen. Or we can use these X-rays to look at very fine details of your bones. So this is a very close-up picture of a hip bone. And it can help you see if that bone has very small defect and to prevent diseases such as osteoporosis. So that's very powerful to use X-rays like these. Other techniques that we use for scientific application are X-rays, absorption, spectroscopy. So what does it tell you? I told you that it's very nice to have an X-ray source with many wavelengths. It's important because if you have a source with many wavelengths, like the one I'm showing schematically on the left, and you send it through a sample to a piece of diamond, to a piece of aluminum, and you look at the X-ray wavelengths after they've gone through that sample, some wavelengths have disappeared because they have been absorbed by the material. And the way the material absorbs the X-rays tells you about its composition and about its structure and about its state. The second technique is X-rays for diffraction. For example, if you have a big molecule or a big protein and you send X-rays onto it, the way the structure of the protein is arranged is going to scatter the X-rays throughout. And the way the X-rays are scattered also tells you a lot about the structure of a particular protein, which can be very helpful to also prevent diseases or discover and make new drugs to prevent diseases. And finally, if you have fast X-rays with many wavelengths, like the X-rays we create with our laser plasma accelerators, well, we can do something that is called pump-probe experiments. So how does that work? We take our X-rays that have several wavelengths. They're fast. We send them through our sample. Some of the wavelengths are absorbed. It tells us a lot about the state of your sample. Now let's say that you try to kink your sample with a little bit of energy. For example, you have a piece of aluminum and you shine it with laser light. Try to heat it a little bit or to put a lot of pressure on it. It's going to change its state and its composition when it do that. And so if now, a few femtoseconds after having done that, we send our X-ray through, then the wavelengths that are absorbed by the sample are going to be different than the wavelengths that would have been absorbed by the sample if it was just in its normal state. So it's very helpful for us to diagnose matter when it's in an extreme state. And with the lasers that we have at the lab, we can put matters in states that are so extreme that these are the states that you would have inside of the sun or inside of planets. So this type of experiment allows us to understand how matter behaves inside of planets or inside of the sun. And these molecules and atoms arranging themselves together with our X-rays from a laser plasma accelerator, we're not only able to see how they were before and after arranging themselves, but we're able to see arranging themselves as it happens, which is why it's very powerful. And this type of research requires using very intense and powerful lasers. There are many of them around the world. This is a map of lasers we have around the world. And we're lucky because we have a few of them in the Bay Area. So that's good for us, right? And so I'm going to finish today. And so what have we learned? What are the things that we've learned today? I hope we've learned that we have a lot of particle accelerators around the world, and these are very, very powerful. They are used for many applications. They use charged particles that accelerate to very, very high velocities. One of the uses of these particle accelerators is to make X-rays for scientific discoveries that are very important. But at the lab, we have found a way to produce X-rays that are even more powerful in a very, very small setup. And for that, we use lasers, just like you'll see in the movie, and plasmas to make new discoveries. And indeed, laser plasma accelerators are even going to revolutionize more the fields that I've presented at the beginning of the presentation: fundamental discoveries, medical application, industry, and national security. And so finally, the great joy of my work is that I work with many people and many great collaborators around the world. And so of course, I wouldn't be there without them today. So I want to thank them. And with that, I probably won't be able to help you with your surfing skills, but I might help you with questions you have about physics. So I'll take any questions if you have any. Thank you. I see one over there. Yes. Yes.
Aren't particle accelerators incredibly dangerous?
So you're asking if particle accelerators are dangerous. All right. So if you're staying near a particle accelerator when it's in operation, yes, it's dangerous because it emits radiation and it's not healthy if you're doing that. But when we do experiment with particle accelerators or when we operate particle accelerators, we're never near the machine and there is a lot of shielding, so either concrete or lead between us and the particle accelerator. And they're also often underground. They're buried underground so that we can protect ourselves from them. Yes. Yes.
So your presentation talked mainly about X-rays. Have you guys been doing more research and trying to mimic the frequency of gamma rays?
Yes, we have done gamma rays too. So I haven't shown the way we do gamma rays. So to do gamma rays in our particle in our plasma, laser plasma accelerators. So I showed you that the electrons are wiggling. In order to make gamma rays, we would have to make them wiggle even at a higher frequency. So we have different techniques to do that, which I haven't shown here, but yes, we've done that, and if you want to know more, I'll be happy to tell you about it. So, yes? Oh, so I told you here, as a kid, I had to have a big surgery without which I wouldn't be walking today. And so I spent a lot of time with an orthopedic surgeon, and he explained to me about his work and everything. So I became very attracted by science. And I also, at home, my parents had a big astronomy book, which I like to look at. And I became passionate about planets and stars. And so I said, I want to either be an astronaut or an orthopedic surgeon when I grow up. And so I went into physics. I studied physics because I thought maybe that's going to help me to become an astronaut or an astrophysicist. And somewhere along the way, I had to do an internship, and one of the professors offered me to build a laser as part of my internship. And I thought it was so cool that I decided that I would want to work with lasers. So that's why I became a laser scientist. So, yeah. So you'll have opportunities that show up. Yeah, if you see something that you like along your path, then you can try and work on that. Yes?
Are there natural objects in the universe that
Are there natural objects in the universe?
Oh, natural, that's a very good question. So there are a lot of objects in the universe that produce X-rays and gamma rays. So in principle, in order to create a laser, you need to excite matter to a state that it's going to radiate that. So I don't see why not it would be possible. It would be possible, yeah. Lasers like the laser we have on Earth, not that I know of, yes. But X-rays and gamma rays, it's observed many times in astrophysics. Yes, or
Last
two.
question.
If you talk about the electrons and how they have to catch the wave,
Yes.
how they have to pick up energy, what is the percentage of electrons that don't make it, the ones that just kind of, it didn't sound like very many of them.
Oh,
It's like it's kind of hard to catch that wave.
yes. So a lot of the electrons are made, most of the electrons are making the structure. They're part of the wave. So for example, it's like comparing the water in the ocean with the amount of water that you have breaking on a wave. So the white water, it's like comparing the white water on a wave compared to all the water of the ocean. So it's a very tiny fraction, much less than 1%, much less.
So I want to stop it here, and I want to announce our 3 random winners of a lab t-shirt, and then I'll invite anybody who has questions to come down here and speak to Dr. Albert, and anybody who wants to use the concessions before the movie to go out to the lobby. So the following 3 people, please go out and get a t-shirt at the lobby. Jojo Gomez from McKinley. I hope I get these names right. Johan Alvarito from Enoch High School, and Danielle Hubrick from Bayi High School. So with that, let's thank